All right, so if you wanted to find a local maximum or minimum for a 2D function, right, when we're working in the 2D world, a single variable function, it was pretty simple. What you would do is you would find the critical points. A local max or min in a function, right, is just when at a local max, your value cannot get any higher if you were to move up or down, right? At this point, if you were to move to the left, you would decrease, and if you were to move to the right, you would decrease. Now, obviously, if you move to the right far enough, you will eventually increase, but at least locally, like right there, you're at your kind of maximum value locally. You can only decrease from there. Same thing here, right? Except it's the minimum. If you move this way, you're going to increase. If you move that way, you're going to increase. So locally, you're at a minimum. And then obviously, if you move far enough to the left, you will start to decrease. But locally, it's a minimum. So local min, local max. And the idea is that, well, hey, at these points, you're going to have a horizontal tangent line, right? And that makes sense. Geometrically, you could see that the point of tangency would be equal to 0. And if it were not 0, right? If it were not 0, that means moving to the left, you would essentially be decreasing, and moving to the right, you would be increasing, right? If you think about like at a point right here, right? This is not a max or a min because the tangent line is not horizontal. If you move to the left, you're going to decrease. If you move to the right, you're going to increase. So when the tangent line is 0 or horizontal, that's when you have no, like, you will have movement, but it's like, you're not going to be, it's kind of, honestly, when you break it down that far, it's kind of unintuitive. But hopefully it makes sense, at least visually, you can tell it's going to be a horizontal tangent line. So that means finding where the derivative is 0. So I would just take f of x, set it to 0, or f prime of x, set it equal to 0 to find the horizontal tangencies, and boom. That's when you're going to have, for the most part, at these x values, a local max or min. And there's an interesting case where you actually might not get one, but I'll talk about that in a second. So in the 3D world, local maxes and mins are defined much the same way. At this point right here, no matter which path you take, whether you go this way, that's the thing about the 3D world, you can kind of take infinite paths, right? We talked about that in limits. But no matter which way you go, you're only going to be decreasing. So it's a local max. Same thing here, but this time, as you can see, no matter where you go, you're only going to increase. But the function will never get lower than this point because it flares out to infinity. Kind of not the endpoint behavior, but this is called an absolute minimum because no matter where you go, this is the smallest your function is going to get, or the lowest z value, right? Now, it's going to be a very similar point or process of finding these local maxes and minimums. You do, in the 2D world, you find your critical point, and then you do the second derivatives test, and you're saying, hey, if f prime prime is greater than 0, that means it's concave up, so we have a local min. And if f prime prime is less than 0, it's concave down, you have a max. We're going to do the same thing, the second derivatives test, not the same thing. We're going to do a second derivatives test after we've found the critical points. And the critical points are when the partial derivatives are both equal to 0. So when partial f partial x is equal to 0, and partial f partial y is equal to 0. When both of those conditions are true, right, you can see at this point, this sort of tangent line, right, if you were to think about like the x and the kind of x direction, the tangent line is equal to 0, and then the y direction, the tangent line is equal to 0. So you have this point of, this kind of critical point where the partial derivatives are equal to 0, and we're going to use a second derivatives test to figure out exactly what kind of, whether it's a maximum or minimum. But just like in the 2D world, you will get an x value when you're trying to find the critical points. When you're finding when the derivative is equal to 0, you're going to get a point, you're going to get an x value right here. And it's going to say, hey, there's a critical point right here. Because at this point, there's a tangent line, right? At this point, it goes from concave down, it flatlines right here with the derivative equal to 0, and then it goes concave up. And we call that a point of inflection. Now, sort of similarly, there's a point. So there's a point where the partial derivatives can equal 0, and there's no, it's not a max or a minimum. and that's called a saddle point. So if you've probably seen a saddle point before, let me show you on my iPad what it looks like, because they're kind of hard to draw, to be honest. But they kind of look like this, okay? So it's like this kind of Pringle shape. Oh my god, I probably messed up the camera. So we have like, I even Googled what function is a Pringle. But you get a kind of a Pringle shape, and that's kind of what I've attempted to draw up here. Let me see if my camera got busted up. No, it's fine. So you can see at this point, the partial derivatives are equal to 0, right? The tangent line in the x direction, or y direction in this case, is 0. The tangent line in the x direction is 0. So it looks like there should be like a maximum in there. Let me just want to make sure the camera's not. Yeah, it's probably fine. It looks like there should be one, but as you can visually see, there's not one, right? Because you can travel up, you can increase, and you can decrease. So there's no, if you go to the side, you can decrease, and if you go up along that path, you can increase. So we're going to talk about how we can identify saddle points as well as local maximums or minimums. So I'm going to talk about the second derivative test in the 3D world, but first, when we were talking about this example right here, finding the critical points, or finding the local max, min, and saddle points for this function, first thing we got to do is find the critical points, which is where the partials are equal to 0. So if we have e to the y times y squared minus x squared, I'm going to take the partial derivative with respect to both variables. So partial f, partial x, pretty simple because e to the y is a constant, and then I'm multiplying by here, negative 2x, right? I'm taking the y squared is treated as a constant, so it's going to be negative 2x for here. And then partial f, partial y is going to equal, so it's going to be, we've got to do product rule here. So I'm going to leave the first function, take the derivative of the second. So this is going to be 2y, because the derivative of y squared minus x squared is, what do you call it? It's 2y, because the x squared is a constant, and then treat it as 1. And then for the next part, right, I'm going to leave this function, but then I take the derivative of the first, which is just e to the y, because it's an e to the x, e to the y function derivative is the same. And I'm looking at, hey, when is a partial derivative equal to 0? Now, here's the thing about exponential functions, they're never equal to 0, right? Because, if you've seen an exponential graph, it never touches the x-axis. So I know e to the y is never going to equal 0. I can divide everything by e to the y, right? I'm not getting rid of a solution. I'm not dividing by 0. I get 0 is equal to negative 2x, and very clearly x is equal to 0. So I know the partial derivative, partial f partial x is going to equal 0 at x equals 0. Now, if you were to see, if you were to try to find the points right here, right, when setting them equal to 0, you're going to be like, wait a second, I have two variables. I'm working with y squared and x squared, and y. I'm working with y's and x's, and I have to solve for when y, what the y value is equal to, right? If I were to graph if I were to graph this, I would actually get a curve, right? Because it's an equation in terms of two variables. This would actually equal a curve, and on your curve, if I were to graph this into Desmos, I would get some weird looking curve, and then every point along this curve will satisfy this equation. But I only want to find the point, right? There's only going to be, a critical point for a couple of points, not an infinite amount. So, think about it. Critical points happen when partial f partial y is equal to 0 and partial f partial x. Both the partials have to equal 0. So there's only going to be a critical point when x is equal to 0. So I can plug 0 into here, if that makes sense, right? Because it's like, I'm looking for when partial f partial y is equal to 0, when partial f partial x is equal to 0. And that's going to be true when x is equal to 0. So I can plug in x equals 0. So I get, once again, I can also divide everything by e to the y, because they're included in each term. So I get 2y plus, now I have y squared minus 0, right? Because x is 0, right? When partial f partial x is equal to 0. So I get 2y plus y squared equals 0. Factor out a y, I get 2. I get y and then 2 plus y. So I have two y values, y equals 0 and -2. So I have found the critical points. Well, how do I tell if they're maximum, minimums, or saddle points? This is where we have to use the second derivative test. Here's how it works. Basically, I'm going to take this is going to be kind of crazy. I'm going to take this second partial derivative with respect to x, multiply that by the second partial derivative with respect to y, and I'm going to subtract the square of the mixed derivative. And that will give me some number. I call it d. Because this is actually, if you think about it, it's kind of, you know what, I don't need to worry about that. Okay, the reason I call it d is because it's actually kind of like a determinant. It's this determinant right here. Right here, if you were to actually compute out this determinant, f of x times f of y minus, these are the same thing most of the time, so it's f of xy squared. Whatever, if you take d, that's a way to remember it, but I'm going to talk about the intuition of this in a second. Point is, when d is greater than 0, that means that when d is greater than 0, that means that if f prime of xx is equal to 0, that means it's there's going to be, if you think about the concave up thing, there's going to be a minimum. If f of xx is less than 0, there's going to be a maximum. And if it's less than 0, that means it's a saddle point. And if d is equal to 0, you can't use this. It's inconclusive. Okay, I just kind of pulled this equation out of my brain. Like, where did this equation come from? I mean, I did show the determinant thing, but like, why are we taking that determinant? This is such a weird second derivatives test, right? Let me talk about the intuition of this. Here's the deal. A saddle point, let's think about this. A saddle point occurs, like in this scenario, a saddle point occurred because in the x direction, right? If you were to look at a cross section, right? If you were to split this along a plane, y equals, along a plane, like y equals k, right? If I were to split this at that point, you would see in the x direction, the cross section is concave down. And then in the y direction, if I were to split it with a plane, the y direction, it's concave up. So f of xx, that's a bad habit. The partial derivative with respect to x, is negative, right? It's concave down. And then the partial derivative with respect to y, the second partial derivative with respect to y is positive because it's concave up. That cross section is concave up. Concave up positive, so positive, negative. That becomes a negative number, and I'm subtracting that by, well, the derivative, the mixed partial derivative, or the mixed second partial derivative, square it, it's always going to be positive. So I'm taking a negative number, subtracting it by a positive number, this is for sure going to be negative. So when d is greater than 0, right, or when the second partial derivatives with respect to each variable don't match, meaning one is positive and the other is negative, this determinant will always be less than 0. And that makes sense. We get a saddle point. So, and in the same way, now this is where it kind of gets confusing. For a local max or min, you can see that the concavity in the x direction, right? Like right here, it's in the x direction, or in the y direction, I guess, what I'm drawing. It's positive, and the x direction is also going to be positive. So both these terms are positive. The only caveat is this f of xy squared term. I'm going to be honest, I still fully don't understand the intuition behind this. The idea is kind of like, well, if your partial derivative with respect to x changes a lot in the y direction, then there's a chance there might be a saddle point, I guess, because it's like the partial derivative with respect to x and the y direction is changing a lot. So, yeah, that's kind of like the intuition behind that's kind of I still need to read up on that. But the idea is that if these two strongly agree, meaning, right, if this product ends up being really big where they're both positive or they're both negative, because when you multiply two negatives together, you get a negative number. You get D is greater than 0, which means it's a local max or min. The bottom line is that when f of x, or if the determinant is greater than 0, that means both the second partial derivatives have to have the same sign, right? Because you're subtracting a negative number, so these would have to be positive. And you can see that, right? It's either positive, positive, or negative, negative. And then you just use the concavity of one of them at that point, right? If f of x, if the second partial derivative with respect to x is positive, it's the same thing. We have a minimum, because if you take the cross section, it would be a minimum. Same thing here, except if it's negative, it would be a maximum. So let's use this. First, I got to compute the partial derivatives, second partial derivatives. So for the for x, right, if I'm taking the derivative of this with respect to x, I just get negative 2e to the y. Hopefully you kind of see that, right? And then I'm also going to need the mixed second partial derivative, so f of x, y. With respect to y, this actually becomes a constant, but it's also like this times the derivative of that, which is e to the y. So I just get negative 2x e to the y. As you can imagine, this will be a little bit more complicated, but it's not too bad. F of the second partial derivative with respect to y. We can do product rule here, so I get 2e to the y, right? Because I'm doing e to the y times the derivative of this, which is 2, plus 2y e to the y. Same thinking, 2y, right, times the derivative of this, e to the y. And then, if you actually look right here, you can be clever and be like, whoa, wait a second. Y squared minus x squared times e to the y, that's just the derivative of my original function. So if I'm taking, or that's just my original function. So taking the derivative is just taking the derivative of this function with respect to y, of course. So I can just use this equation, right? So I get 2y e to the y plus y squared minus x squared e to the y. Hopefully that makes sense, right? This is my original function. So when I'm taking the partial derivative with respect to y, that's just the same thing as taking the partial derivative of my function with respect to time, which I already calculated. So I just sub that in for my product rule. Okay, that was quite a lot, but now we know our critical points, 0, 0, and 0, negative 2, right? Because x is 0, and those are the y values. So I can just test them now. So CP, critical points. Let's work this out. So if I were to do, let's start with 0, 0, f of xx, or the second partial derivative with respect to x. F of, oh my god, I hate saying that whole jargon. There has to be jargon for that. Like, there has to be a shortcut way. Whatever. When I plug in 0 as y, I just get negative 2. And f of xy, if I were to plug that in, I get 0, right? Because when I plug in x as 0, the whole thing becomes 0. Oh my god. So now I just got to find this second partial derivative with respect to y. This is actually not too bad because I'm working with 0, 0. So when I plug in a 0 here, this just becomes 2. There's a y here, and a y minus x. For all those terms, that just reduces to 0 because I'm subbing in a 0, right? Y 0, y is equal to 0. 0 minus 0, right? So when I plug in a 0 here, I just get 2, right? 2 times e to the 0th. E to the 0th is 1, so I get 2. So when I'm doing my second partial derivative test, right? 2, so negative 2 for the xx, 2 for the yy, you can already tell what it's going to be. It's going to be a saddle point, right? I get negative 4. That's less than 0. That means I have a saddle point. So at 0, 0, there's a saddle point. Now, if we were to do this for negative 2, right, for y equals negative 2, it's going to be a little bit more annoying to calculate. I guess not for the mixed second partial derivative, right, because x is still 0, so this whole thing turns 0. In here, you get negative 2 times e to the negative 2. And then here, when you do this for at y equals negative 2, this is kind of a little bit more annoying, but you're going to get 2 e to the negative 2 when I plug it in. 2y e to the y plus 2y e to the y, that's just 4y e to the y. And if my y value is equal to negative 2, so I get negative 8 e to the negative 2, right? Right, 2y, so in other words, 2 times, that's negative 4. So negative 4 e to the negative 2 minus negative 4 e to the, let's get negative 8 e to the negative 2. And then here, this will become negative 2 squared is 4, and then x is still 0, so I get 4 e to the negative 2. This whole thing turns into this whole thing turns into negative 2 e to the negative 2. So when I were to compute my partial derivative this time, really I gotta look at the signs, but I'm saying 2e to the negative 2 e to the negative 2 times negative 2 e to the negative 2. You're gonna see, and then minus 0, that's gonna be equal to 4 e to the negative 2, which is greater than 0. So yeah, that means there's gonna be a max or a min, and I just use the concavity, right, in the x direction or y direction. It's gonna be negative, so that means there's gonna be a maximum, right? If you think about how it's gonna be concave, the cross section will be concave up. So there's gonna be a local max. And if I were to show this to you, this actually ends up being the case. Let me just show you on my iPad. So if I were to show you on my iPad, you could see pretty interestingly, at this point right here, at the origin, 0, 0, there is a saddle point. And then right here, there's this kind of bump, right? There's this kind of bump right here at 0, negative 2. And that is actually the, that's the local maximum, right? It kind of bumps up and kind of, it kind of like bumps up, just not as pronounced. I was going to do this example because it's kind of cool and what 3 positive numbers sum up to 100 and have the largest product, but honestly, this has already taken up like 20 minutes and I don't want to waste much more time, but I would like try it. I would suggest you try it. My hint is, think about those kind of problems that we did in Calc 1 or 2 or Calc BC, whatever. We did problems like that, optimization problems. And think about how you would approach it in the 2D world and try it in the 3D world. Constraints are important. Okay, so let's talk about absolutes. So you can find absolute maximums and minimums on a sorry, I'm a little bit out of breath. You can find them on a closed set. So for example, if you had your function, right? If you had your function, you can actually, this is my good mark. I'll use a bad one. But if you have like some sort of function, you can find local maximums and minimums, right? On a region, right? On like a certain set. So in the 2D world, we found absolute maximum and minimums on a range. So like from x equals negative 2 to x equals 8 or whatever, right? Well, in this time, we do it on like a set of x, y coordinates. So maybe like on a region with coordinates or triangles with these like certain coordinates as vertices, right? So for all points, right, if you were to like extend this like kind of upward, for any z values in this kind of region, what is the local max or absolute max or minimum? So to go about doing that, here are the kind of steps you need. The first step is in this region, right? So in your region, if you're finding it like within a triangular region or whatever, think about the interior. What are the critical points? So step one, find critical points inside region. Because our critical points can tell us if there's an absolute max or local max or minimum just for the entire function. The second step is check your corner points, right? your corner points, right? Just like how we check -2 and 8, the corners could also have just a maximum or minimum, even if they're not necessarily a local max or minimum. And then the third step, this is different from the 2D world, is also you have to check the boundaries. The boundaries along the side, there could also be a max or minimum. We actually have to make it a 2D max or min problem to figure out whether the boundaries have any maxes or mins. So this is all kind of abstract. Let's try an example and see if we can make sense of what we're doing. So let me just find it. The problem in question. Okay, this is kind of a crazy one. This is a slightly crazy one. Let's say we have f of xy is equal to 3x squared plus 2y squared minus 4y. And we want to find what the absolute maximum minimum is within a region in the xy plane bounded by y equals 4 and at y equals x squared. Okay, so this is our region. Area bounded. So what this looks like is on the xy plane, we're going to look at xy coordinates that belong in this region. So this is xy squared, and then y equals 4 will be a vertical or a horizontal line. When 4 is equal to y squared, that's at x equals 2 and -2. So it's these points right here that we are considering. Let's find the critical points inside the region. So I'm going to do it like this. Partial f partial x is going to equal 6x squared, right? That's pretty simple. So when x is equal to, or 6x, sorry. And then partial f partial y, or just, yeah, partial f partial y, we get 4y minus y, or minus 4. This is when y equals 1. So x equals 0, y equals 1. Yeah, that's essentially it, right? There's no, that was the entire thing, right? Yeah, we're good. So there's only one critical point, 0, 1. So CP, I'll say like step 1, we just gotta find, we don't even have to use a second derivatives test here. We could use a second derivatives test, but we're not really concerned about whether it's a local max or min. We're just seeing, like, it could be a saddle point for all we know, but we're just throwing it as a candidate. This is called candidate test, right? This is a possible candidate for being an absolute max or min. So f of 0, 1, when I plug in, a 0 here, I get 0 plus 2 minus 4, so I get -2. That's one thing I'm going to consider. So for the second point, we're going to check corner points. There's really 2, right? We have really 2 corner points, but if you'd like, you can also throw in 0, 0. The reason being, one time I did a problem like this, where the region was a circle, and for the solution manual called for using the corner points of the circle as not corner points of the circle, but using these like two, like it was 2 0 1 0 0 0, or it was 0 2 1 0 0 0 0 -1, using the outermost points from the origin or from the center. I played they're all equidistant. It was just like the 4. I hope you know what I'm talking about, and it said include those, and so I'm gonna throw that in there too, using the kind of point on the parabola here. So we're gonna use a corner point. So f of 0 or 2 0 is gonna equal 3 times 4, so 12. And then f of -2 0, I also get 12. And then the zeros. Oh wait, no, I'm so silly. It's 2 4. obviously, because this is how y equals 4. Man, I thought my life's about to be so easy. 2 times 16, because that's 4 squared, minus 16. So I just get 12, right? 2 times 16 minus 16 is just 16. So I get 12 plus 16, which is, shoot, why am I 28? Same thing here, right? It's really the same thing. I'm doing 12 plus 2 times 16 minus 16, so it's going to be 28. And then 0, 0, it's going to be 0. So either way, that wasn't going to really help us, but because that's already in between the lowest possible and highest possible. But good that we did it. Now boundaries. This is the part where you want to kind of pay attention. You need in this case, there's only kind of one-ish boundary. It's just the function. Oh, maybe, never mind. Okay, never mind. I was about to say something, but don't worry about it. Yeah, okay, don't worry about it. So if you had a region like a triangle, what you would have to do is for each of the side lengths, for what I'm about to do, you have to find equations of lines for these side lengths. So what I would do is I would take one of the points, right? Maybe this is AB. I would find the slope of the line, and then I would use point slope form. So if the slope was m, by calculating using that point and that point, I would get y minus b equals m x minus a. And that would be my sort of function for that one line boundary. And it would be a different line, obviously, for each one. But I would use this equation for this step I'm about to do. And in this case, it's a parabola, so I'm going to use y equals x squared. What I realize is along this curve, all the y values are going to equal x squared. So this would be the same thing as doing f of x squared. What this does is it gives me the points along my 3D function, but just along that curve, if that kind of makes sense, right? Like if you think about if this was our surface, I'm just going to erase this, but if this was our surface, then I'm really doing all the points like so, right? This is in the xy plane. So it'll be all the points along that point, right? All the points on the surface, right? Along the curve. That's what f of x squared is doing. And in I would just plug in this right here if it were for like a triangle, for example. Whatever my function is in terms of y. So I would just substitute everything in here. So 3x squared, all the y's become x squared. So I get 3x squared plus 2 x squared squared x to the fourth minus 4x squared. So this just becomes 2x to the fourth minus x squared. And what I can do now, this is just a single variable function. So I can just minimize this, just taking the derivative. So f prime of x equals, if I were to take the derivative, I would do 8x cubed minus 2x, and then I can factor out a 2x, so I get x squared, or 4x squared, what is that? What's 4x squared minus 1? So I would get, if I were to solve this out, I would get x equals 0, x equals negative 1/2, and x equals 1/2. So, and then, I got that from just, setting this equal to 0 and then solving for x. I've already tested x equals 0, but now I have negative 1/2 and 1/2. And obviously this is squared, so I really only got to test for one of them. So f of 1/2, if I were to plug this back into x squared, right, it becomes 1/4, right, because this is a point along that curve. So I would get 1/2, right, because I'm doing, or 1/4, right, because I'm doing 1/4 there, plus, right, or 1/2 squared, right? 2 times, now I would do, for 1/4 squared, I get 1/16 minus 4 times 1/4, that's just going to be 1. So I get 3/4 plus 1/8 minus 1. 3/4, so this is really the same thing as 6/8. So this is 7/8 minus 1, which is -1/8. And that's the same for -1/2. So I can tell by calculating all the points, the maximum is going to be 28, and the minimum will be -2. So that is kind of how you find the absolute max or minimums. Yeah, thank you for watching. This has been kind of a long lesson, but hopefully this process is pretty familiar from Calc BC or Calc 1, Calc 2, whatever, and hopefully it makes sense. So yeah, thank you for watching.